חסר לי רק אלמון. Okay, so what we're going to do today is basically look into one of the most famous conclusions of quantum mechanics. That's the fact that when we measure some physical measurement, we might be in a situation that another physical measurement is undetermined. Okay, you've heard about it. What's it called? Heisenberg's uncertainty principle. Truth to be said, it's not surprising at this stage. Once we know that a measurement is the result of possible measurements, are measurements that correspond to eigenvalues and eigenvectors of a particular operator, and not every two operators you can describe with the same basis. So if you measure one operator, you get a superposition of states for the other operator, therefore it's undetermined. But historically this came after the uncertainty principle, and the popular conception of quantum mechanics, it remained one of the main principles of quantum mechanics, although it's a direct result of our description of quantum mechanics as possible measurements, our own measurements of eigenvalues corresponding to eigenvectors in the given. That was formulated by Dirac a couple of years after Heisenberg came to this answer. Okay, so what we're going to do is, first of all, prove the formulation of the uncertainty principle. Which is first we will have to define what is delta T and what is delta X. And basically, what does it tell us? It tells us that for a particular wave function, the smallest result of delta x times delta t has to be at least h bar over 2. For a particular wave function, it could be much lower. So we'll prove this statement and then see how to construct the minimal wave function for which it's equal h bar over 2. Now, why is that important? Once we're dealing with some kind of quantum manipulation and we want to create a wave function with minimal uncertainty, it's very important to know this. Then we will know how to create such a wave function. Okay, so let's start. In general, delta A or delta A squared would have been dealing with the regular statistics. What does this mean? Probabilities. This is the variance. And this is average over different realizations, or I mean set. Here it's quantum mechanics, so what someone would like to guess what this symbol means? It's a shorthand for doing this calculation for a particular waveform. Well, it's not surprising. What can I do with an operator? Use it on a wave function. Now, which wave function to use here? Depends on your needs. Take another operator, D. Perform the same calculation. Choose a wave function. Doesn't matter. Okay, I'll write it down more explicitly. No, it's not the variant. That's why I insisted all the time to explicitly state that that's for a given wave function. The variance of A and the variance of B is meaningless unless I'm telling you on what state of the system I'm using. It's just an operator. What is a variance of an operator? Undefined. I know what is the variance of a measured property. And the measured property depends on the wave function. Some of you have heard the concept of entanglement. Entanglement is defined for a specific wave function. It's not a general concept. I can't ask what is the entanglement of a system. I can ask what is an entanglement for a given wave function. Same thing here. I can't ask what is the variance of the operators. I can ask what is the variance of the operator for a given wave function. So the same thing here. I want to rewrite it a bit differently. Why am I allowed to do it? Excuse me? And why does it have to be a permission? It's an operator that measures something, therefore I'm allowed to do this. Should have written here. Yeah, but it's meaningless because it has to be same thing for me. Just to be sure that we are all on the same page. What is this? Expectation value for the same waveform. You're consistent. You're using the same. This is an operator.
Okay, I thought you meant also.
The entire thing is a number. It's a result of a measurement.
Okay, I thought you meant.
Okay, now so what's written there? The commutation relation AB minus BA. One over 2I, we'll see why is that. Absolutely. We see that if A and B commute, it could be 0. If A and B commute, the result of the commutation relation is 0. And then I can measure something with the same variance in A and B, or no variance in A. Well, of course, if it commutes, it's the same. You can write down the same basis. If you can write down the same basis, if you measure one, you measure the other. No uncertainty. How is that connected to that? We'll see. No. This is a specific law for delta x and delta p. This is general for any two operators. And if you remember, the commutation relation between x and p is h bar over 2. Up to and now. Okay, but we're now trying to prove this state. So, what's delta A? We'll just copy what's written here. And to make life easy, we'll put square here. just wrote down the definition and decided to move the Hermitian operator b minus b operator minus average b squared before the psi complex conjugate. Okay. Next. Okay, I'm looking on this guy, and it reminds me the following integral. Someone guesses towards where I'm going? This is not exactly what's written here. Okay, Schwartz inequality. This term is bigger or equal basically it tells you that if you square before you sum, it's larger than if you multiply and then sum. Very simple. Let's assume we have one function is 1 and minus 2, f is 1 and 2. Let's sum it up. 1, 4, 5 times 5, 25. The other hand, if I do this guy, I have 1 times 1 is 1. Minus 2 times 2 is minus 4. 1 plus minus 4 is minus 3. Minus 3 squared is 9. And very surprisingly, 25 is larger than 9. So this is just the integral form of this inequality. Actually, it's not. It's almost trivial. If you multiply functions that could be plus and minus, first square those functions and then sum them, or multiply them and sum them. Of course, in the second case, you only can get a smaller result. Okay, and this is just the Schwartz inequality. Okay, so someone can guess when it's equal.
equal to F1.
Correct. And I can always multiply it by a constant because it doesn't change. So that's equal, anything else is smaller. Okay, so how do we use this connection? So instead of writing this guy, okay, that's basically Schwartz inequality. And okay, so let's continue here.
Could you explain how did you get to the delta A about A?
Okay, let me write it again. I think I had here a mistake. Did someone noticed? I'll write it down even simpler. Okay, that's just by definition I labeled it here with it noticed, and that's we have shown through the Schwartz inequality larger or equal to okay. Good. So basically, we should write down the operator A minus average A times B minus average B. These two are scalars. Is A times B Hermitian? Refresh memory from two
I think
lectures back.
I think so. If A and B are Hermitian.
No,
No.
definitely not. We have shown an example, x and p. X times p is not equal to p minus x. We have seen it for matrices. The matrices can be completely Hermitian, and the multiplication is not necessarily. What we can do is rewrite any non-Hermitian operator, the sum of that Hermitian and in one of those boring sections of mathematics that we did in the beginning. So let's exactly do it. Okay, first of all, it's correct. Add, so you get this term, and this term is in minus and falls off. So it's correct. Second, as we have shown, all of this operator, which we will term as f, is Hermitian. Simplest reason, we have A times B and B times A, and A and B is Hermitian, so it's Hermitian. We have also proven it when we wrote the definition. And this guy I'll add here. And this guy is also Hermitian. Again, we proved this a couple of lectures ago. Okay, it seems that I'm just bothering you with long and not very clear algebra, but what is C exactly? AB minus BA and all other falls off.
That's the, I don't know what it's like.
This is exactly I times the commutation relation between A and B.
Oh, that's
So back to our beginning point, delta A, delta B square. Okay. Didn't do anything, just wrote it down back and the form that we had. End of story. There's no rules that the average of f can't be 0. But if it's not 0, it's larger than 0, right? Okay. So it seems that we put a limit that is much weaker. Highly better. Like we twice wrote large equal. Right? Here we omitted the term. Here we omitted the term. That we proved the statement. Okay, in a moment we'll do an example for x and p. But in general, what are the conditions that will get minimal uncertainty? One of them is going back to Schwartz inequality. As Joseph told us, if f is equal lambda times g, it's not larger, it's equal. Okay, what does that mean for our structure here? It means that has two conditions. Now lambda just so the Schwartz inequality will be minimal, equal and not larger. The second, you remember that we threw out f. Yes, we had f average square and we said, so we need the second term or if you want, or Okay, what did I do here? You remember, average f we need to set to 0 in order not to get the second term. So I just wrote it down explicitly using this connection. Because if you remember, we had a times b, and so I'm changing it to square and square and taking half of each time. And this is a minimal case where delta A, delta B is half IC. And then I just substitute it here and get the value of lambda that I need. So basically, if I can write down this connection and this connection, I can get what is the minimal uncertainty for any given psi. Now we'll do an example for x and p and find what is the minimal uncertainty wave function, which some of you have guessed in the end of the previous lecture. Gaussian, as you have guessed. Okay, so that's our next goal. Excuse me?
Leave this spot.
Sure. Okay, so we're working with 6 and p. Okay, some of you may remember that we did it already. Let's see the result for any psi. Okay, so what's this commutation? What is the result of the remaining integral? What? Because any wave function in your Hilbert space must be normalizable, so the result in this case doesn't depend on the wave function. So we got minus 1 IH bar. Stick it back in the C, and we get which is the statement which we started with in the beginning of the lecture. Okay, but this, it's not necessarily equal to h bar over 2. It's equal or largely. Now we're trying to find a wave function for which this uncertainty is exactly equal h bar over 2. Okay, so there. Oh, I wrote down the condition for which the Schwarz inequality is equal. As we said, the first condition. What is P0? Just a notation for P, average P. It's a number. What is x0? Notation for average x. Okay. But we know also what is lambda in order to be minimal. That's what we did 5 minutes ago. Okay, so what am I remaining? What do I remain with here? Differential equation. case, that's it. Gaussian is the solution of that equation. Now from this, go and perform the derivative here, compare it to what comes out here, and you'll see that it works. Now, looking on this equation, what do we get here? First of all, one Gaussian. Is it a wide or a narrow Gaussian? Delta x defines the width, and it could be wide or smaller. The wider is it in x, the smaller is it in p. So delta x times delta p is h bar over 2. But we can play around. We want more. Second, if I didn't have this term, what would be? No need for mathematics, just logic. Operator for p has an imaginary curve, and if the wave function doesn't have an imaginary curve, so that's the reason why we have here this additional phase effect. Without it, would p, for the case that p0 is equal to 0, if we measure the momentum of this wave function, will we get only 0? This point should have started flowing quickly. It's uncertainty. We can't have delta p equals 0 but when delta x is 5. Right? On average, this wave function doesn't change. When we measure after the measurement, this thing. So basically we have here all Quantum gauge. Okay, one general additional general conclusion that we can pull out of the wave is after that, after the break, we'll go over to the did
The well?
not connected to wells.
Oh, Hamilton.
Maybe the equation is an equation on a Hamiltonian. Parenthesis. Guy committed suicide. We forgot he committed suicide. We have shown behavior of derivative of x is equal to the average value of p divided by n. Okay. So this is just a generalization of what we did there for an explicit case. So, in general, equations of motion, as in classical physics, the x to the t is something or something or other, right? So I'm doing a derivative, a time derivative of some average result of an operator, of the expectation. Okay. Let's write it down explicitly. Nothing beyond using definitions of derivative of a multiplication. And of course, what is minus IH times time derivative of psi?
E?
That's only from stationary. That's the general, that's a Schrödinger equation. So I can replace minus IH bar d to the t by H dagger, but it doesn't matter. H dagger is H. Can replace this guy again by the Schrödinger equation, and I end up with So, this is another way of writing down how the average of some operator develops with time. Just perform the commutation, write the expectation value, and that's a derivative of the average or the expectation value of this operator. Now, if A is not dependent on time, that's all there is. If it depends on time, so this. What else can I learn out of it? And that's actually, we didn't need this calculation to show it. Makes sense also without this. Well, actually, not only makes sense, you can prove it even without this calculation. If A commutes with H, the average of this operator doesn't change with time. Not surprising. Someone can come to the blackboard and prove it in another way. Volunteers?
I don't think I can prove it, but I'm just saying, throwing hands, if you say that they are commutative, then you can span the same side using
That's the first.
buffer,
That's the
and then
first
using
step.
and then using orthogonality, right?
Even simpler. I don't need orthogonality.
You get here, zero.
All I need, I'll write it here.
Oh, you would get the same side because you use the eigenvectors.
Right.
Okay.
So any wave function I can span in the basis of energy. Okay? But this is also the basis of, let's call it A. So, if I want to know what's the average of A, since the thing doesn't depend on times its derivative is 0. So I didn't even need all these steps. I could go from the point of view of basis. Okay, so we'll have now a break and move to a few examples of problems in one dimension. Again, we'll try to get more general conclusions, and in the recital you'll get specific examples. And hopefully, in the next lecture, we'll get to harmonic oscillator, which is the most important problem in physics in general. Okay, so let's reconvene in a couple of minutes before half. Okay, so one-dimensional problems. Okay, the simplest problem will be, excuse me? A free particle, exactly. Okay, so I can write down and get the solutions. In this case, it's very easy. But I don't even need that. Why don't I need that? Because I've already solved the eigenvectors and eigenvalue problems of P. And eigenvalue and eigenvectors of P are also eigenvectors of P squared. Some of the first lectures we have proven that if we know the eigenvectors of some operator, this operator to any power, these are also its eigenvectors. So are the solutions of the Hamiltonian. Don't believe it? Check. What are the eigenvalues of the Hamiltonian? Well, if I know the eigenvalues of P, and I use the connection H bar K is P, so the eigenvalues here are P squared. And basically, it's a continuum. Any K or P can be a solution, but the energies have a lowest eigen value, which is 0. For either K positive or negative, the lowest value, because it's squared, have values between 0 and infinity. And, well, we have always this problem that these are not really the basically wave functions in our Hilbert space. It's Dirac normalization, but we swallow it. You really can't stand it. Put it on cyclic boundary conditions. Put it on a ring, and everything's good. Okay. Actually, I would like to point a problem, and you'll do it explicitly in the recitation, where actually this type of behavior is reasonable. And these are scattering problems. What are scattering problems? We send a stream of electrons, have some barrier in their way, and ask how much is transmitted and how much is reflected. This case is very similar to the concept of a wave function, of wave transmission and reflection. And in this context, e to the power ikx is a very reasonable solution. And then, in general, and you'll see explicit examples with a teacher assistant, it's basically you have some barrier. You send a stream of electrons, eikx. What do you do here in regular classical waves?
We need the potential to be higher.
No, the potential is a potential.
Classical.
Yeah.
Well, you have the incident theta, and then you get the transmitted and reflected.
You have some reflection. And that's all that interests you. What do you want really to know? Well, r squared plus t squared absolute value has to be equal 1. And it depends on your incoming energy, and mathematically it's to sew up boundary conditions and solutions. Okay, so you'll see many examples, but I want to talk about the physics here. Okay. First of all, very general, this type of question is the bread and butter of high energy physics. Why? What are they doing in most colliders? Take a stream of electrons, protons, or more exotic particles, send them at high velocity, get them to scatter of something, and analyze what comes out. So basically you can do a whole formulation of quantum mechanics which actually doesn't even look on what happens here. It just wants to answer questions of what I measure in my detectors far away from the collisions. That's a scattering formulation. So it's a very important and productive way of doing problems, and basically the basic entity here is you put in the wave in one direction, you get it out in two directions, you'll have here a matrix connecting them. That's a scattering matrix, and once you know the scattering matrix, you solve the problem. Okay, so as I told you, you'll get many examples of this this behavior in the recitation. Just another couple of words on physics. Will I get scattering if I'm above the barrier? That's the big difference between quantum mechanics and classical physics. In classical physics, I'm asking you, when do you pass the barrier? Only if my energy is above here. If I'm below, I don't pass. If I'm above, I don't care about the barrier. But when I'm doing a wave equation, let's see what happens to this equation when I'm looking only on the area of the barrier. Okay? So instead of this equation, what is the change there? And forget about what's happening everywhere else. Well, what changes here? We know. This is not zero, this is some value, right? So are these eigenvalues still good these eigenvectors, are they still good eigenvectors? No. At this point, we're well versed in finding ways to answer it, or at least we should be. If I want to know if it's covered by the same eigenvectors, what do I do? Commutation relation, right? In this case, it would be, let's call it H0, not to get confused. Now the Hamiltonian is the whole term. as previously because it's constant. It's a number. So these are still my eigenvectors. Everything's good. The only thing that changed is the labeling of the eigenvectors, or if you want, the energy. Right? That's the only thing that changed. Okay, just pulling out the square root and playing with the left and right. What does it mean, basically?
Well, it depends on V0, but K could be imaginary.
Yes, but before that, even if K is not imaginary, the value of K changes between here for the same energy is conserved. Here, K is larger than here, in this area. If I'm just building the solution piecemeal. So here I have K and here I have some K prime. Here I'm back to K. So I have three solutions. Each is a ikx with the regular square root of 2me over h bar. Here I have K prime, which depends on V0. And here I'm back to the same value of K. And I have to sew up the solutions on this boundary and this boundary. That's all you'll do there. But the conclusion is that you have a different K going through this region, meaning two things. When you try to sew up the solutions, not always you can have a solution that goes through directly. Sometimes you have to have also a returning component, meaning that you can get scattering here and here, even though you're at an energy that is higher than the barrier. So having a barrier even at higher energies makes a difference. If it's so high that it's negligible, if the energy is so high that the barrier is negligible compared to the particle's energy, then you won't see a difference. But at lower, and you'll do exactly the mathematics, sewing up those solutions is mathematically cumbersome, but can be done. The second part of the solution is what happens in this region. Well, energy is smaller. So I have here an imaginary term. So instead of e to the power I k, k is imaginary, I have an exponentially decreasing function. So it means that in this region, my solution goes down, and if I solve this solution and this solution, I can still get some transmission. But the deeper in the barrier I am, the stronger is the exponential decrease, less is transmitted. And this is the famous tunneling. I go through this barrier, although my energy is lower than the height of the barrier. If I had an infinite region of the barrier, nothing would come through. I have no solution. But for a finite barrier, I can have some probability to go through. And these are the two main physical results that you have to keep in mind considering considering barriers in 1D. Yep.
I'm gonna ask you later.
If you think it's of general interest, ask now.
Oh, it's a little bit off topic.
Okay.
Oh, it's
No.
no. If you say that, you said that if the tunnel is infinite, then
The barrier.
the barrier, sorry, is infinite. Then you said that it was tunneling and everything that comes inside wouldn't come out.
Will be reflected, that's it.
Or will be reflected. Okay. Then never.
No, it's not getting stuck in.
Oh, it's not infinite.
No, it's returned.
Okay.
I don't want to go into the philosophy of virtual particles and so on. The mathematical solution is you have here a function, but then r here is 1.
Okay.
Everything is reflected if it's infinite.
So it's like okay.
Other questions? Okay, so except for really solving such problems that we do in the recitation, we said all that is to be said about a free particle or a particle that is built out of a combination of constant potentials in different regions. Because there it's just treating boundary conditions and that's it. What comes after free particles? Particle in a potential. And before we go into specific forms of potentials, that one of them actually you're already well versed, infinite squared well, I want to give some very general properties of potentials in 1D, which turn out to be very useful when you're trying to solve something. First of all, you can check if your results are reasonable. Okay, let's draw, let's say, the most general potentials that I can think about in 1D. So I'm drawing V of x, and here I have x, and it will start in minus infinity in some value. And in the meantime, I'm keeping one minimum in the potential. Okay, so that's a general 1D potential. Starts at V minus at minus infinity, gets to V plus at infinity, and has some shape with one minima in between. All others will generalize out of analyzing this problem. Okay, I'll give some very general observations. Not all of them I'll prove, but at least they make sense, and some of them I will prove. Okay, for energies that are larger than V minus, and I'm assuming that V minus is larger than V plus, the way around, just to find it the other way, we have a continuum of solutions, and they're degenerate. What do I mean degenerate? For each solution, we have two eigen functions that correspond to it. If you have problems to imagine what it means, go back to the simplest case, which is a constant potential. There, it's always the V minus, and the solution for K and minus K of two solutions with the same eigenvalue. So it's a continuum, exactly like free. So from here above, details are different, but the general behavior is the same as a free particle. Continuum spectra and degenerate, plus and minus K. You always have two solutions for each energy. Okay, now, in this case, we have a continuum. Nothing stops it at the plus infinity, no potential, but degeneracy is killed. So we don't have two solutions for each eigenenergy, only one. Keep this annotation, so I'll call it V0. So let's take an example that I've already mentioned. Coulomb potential, let's say in 1D. Okay, this is a Coulomb potential.
Okay, so this should go. Oh no.
For this case, E V minus and V plus let's
Yeah, absolutely.
exact put absolute value here. Okay, in this case, there's no difference between. So above we have a continuum degenerate solution, meaning that an electron that is kicked out of a hydrogen atom, or if the hydrogen atom becomes ionized, behaves essentially as a free particle. Not exactly, because if you scatter above a hydrogen atom at an energy that is somewhat close to zero, you'll still see an influence. The same as you see some influence, but it's degenerate and continuum. Below, you have discrete values, and actually, as you get in this more and more dense. And you'll have here some minimal solution, but we'll get to that. Okay. So you get some kind of potential. You at least know how your solutions should look like. If you get here the degenerate continuum solutions, you know you did something wrong. You got here discrete solutions, again, you did something wrong. Now, I'm not going to prove these statements. It has to do with the boundaries and a bit of a delicate mathematics that I don't want to go into here, but it's quite straightforward. I want to look a bit more carefully, because it has also somewhat more physics, on another property of one-dimensional potentials, and that's Okay, let's go back to what you're supposed to know from 1D particle in an infinite box. Okay, you have hope that's no surprise to anyone. If I draw it, so I take okay. That's, and so on and so forth. So for the ground state, we have 0 cuttings of the x axis, right? For the first excited state, 1. For the second excited state, 2, and so on and so forth. Well, you can tell me, well, we know what's a sinus. We don't need to say that. The interesting thing, this is correct for any one-dimensional solutions of the potential in the discrete region. But I didn't, it's not sinus, but it cuts the x-axis n minus 1 times. For the first one 0, for the second one 1, and so on and so forth. That's known as a oscillation conjecture, theorem, whatever you want. Theorem, actually, because we shall prove. Why do we prove it? 1, because it's not too hard. 2, it's a very, let's call it, neat and even has physical insight. So what am I saying? I'm saying that this structure remains correct even if the potential doesn't correspond to hard wall, even if it's not described by a psi. For example, for the harmonic oscillation, we will do in the next lecture. Okay. Okay, to prove it, let's meet an operator that when you first meet it, it's very strange that it's a physically measurable operator. And that's the parity operator. does this operator do? Any operator operates on a wave function and returns a different wave function. Okay. It's definitely an operator. If it's an operator, we need to find its eigenvalues and eigenvectors. Now it should be for you a knee-jerk reaction. You see the operator, what is its eigenvalues and eigenvectors? Once you understand that, you're in the game. Okay. That's an eigenvector and eigenvalue equation. Well, how do we approach it? There's one thing that we know. If I apply this operator twice, what do I get?
The same thing.
The same thing. But I can go here and perform it and look on the result if it's an eigenvector equation. And I'll leave you as homework to prove that it's Hermitian. And if it's Hermitian, what is the result? What could be lambda?
1 and minus 1.
Only 1 and minus 1. If it wouldn't have been Hermitian, it could be e to the power I. Actually, if I'm looking on this equation, it can't be e to the power I anything. Actually, I proved already here, it's like homework, that it's Hermitian. The only two values of lambda that can be is either 1 or minus 1. E to the power I theta doesn't work here because it's squared, it's not absolute. So actually, I've already proved that it's Hermitian and can be amazed, but any new elementary particles that they find, first question is, what is its parity? Because it's an observable quantity, because it's a Hermitian.
What does it check? Symmetry.
Checks symmetry of the particle.
So you can use it not only on the x-space vector?
Right? You can write it in general, r to minus r. Putting it here.
Oh, okay.
To x just because we're working in one dimension.
So you can derive new operators from it if for example, conservation of momentum, right? If you know symmetry.
Exactly, conservation of parity or anti-parity.
Okay.
If any one of you have read general physics literature, the standard model violates parity but conserves CPT. No one heard about it. Charge, parity, and time reversal. All particles in the universe, if you change their charge from plus to minus or vice versa, change their parity and send them back in time, are symmetric, have the same solution. Meaningless, but just to show you that this very mathematical concept does have physical applications. Okay, so it's 1 and minus 1, we proved that it's hermetic. Why? Because the eigenvalues are real numbers. So it's hermetic. If you remember, we said it at one point. Hermetic have real numbers, and if all the eigenvalues are real, it's hermetic. Okay, great. So what do I do with it? Okay, now I can play the whole game that I know about bases, on bases that are relevant to the case where I have this parity symmetry. Okay, let's. What are the eigenvectors of this operator? We know already the eigenvalues. Well, by definition, back to 11th grade mathematics, you have even and odd functions. An even function is a function with parity corresponding to eigenvalue of 1. And an odd function is one that corresponds to an eigenvalue of -1. What else do we know? Well, something that we're using all the Paris courses. Orthogonality. Okay, so if you meet a mathematician and he asks you why the integral of an odd function times an even function is 0, oh, there are orthogonal eigenvectors. Nothing more to add. Yeah.
If so, if I have two real odd function. Oh, never mind. Okay.
Don't jump to conclusions.
No, sorry.
Yet. Let's say you have a Hamiltonian. Does it mean that the Hamiltonian, the solutions are even or odd? No. Only if the Hamiltonian is commutative with the parity operator. So, if I take this guy, are the solutions here even or odd?
Sine odd.
Yeah. But look on the potential, it looks symmetric. So how can that be true?
It's like you said earlier, it's like a phase, no?
It's really a phase, or in a simpler way, well, if you do parity on this guy, mirror symmetry goes to minus L. So the Hamiltonian itself in these coordinates doesn't obey parity. So it's not commutative. But I could easily change the notation of the axis to this, and that would conserve parity. Why don't we do it? Because then it makes life a bit more complicated in a sense, because then you have solutions that are sine and cosine. And as long as you don't mess with parity, it's nicer to get just sines instead of these solutions. Okay, let's now do it mathematically. Dimension. just wrote it down. Okay, I wrote down the commutation. Now in general, in one dimension. This part depends on the potential. So, if I'm continuing from here, so if Vx is even the result okay. So the eigenvectors of H and eigenvectors of the parity, in this case, share the same basis. So conclusion, any eigenfunction of the Hamiltonian in this case has a defined parity, because it's also a basis of the parity operator. So if I have an even potential, the solutions have a defined parity. Even or odd, I don't know. But they definitely have the same parity. They have a defined parity. Okay. Next meeting, we'll see why is it relevant to the oscillator theorem, and we'll move to the harmonic oscillator. Okay, we'll stop here.
Thank you.
Thank you.
Okay.